This is Algebra 2 with trig, 6A.3. We're going to be talking about the function e. So the natural base of e, it's an irrational number. Here's a ton of the values of it. 2.718 is what we typically think about it as, but it does go on, just like the number pi goes on forever. This is a number that goes on forever. It's irrational, just like pi. We can do a lot of things with e. We can treat it just like a variable, even though it's not actually a variable, but we can treat it with the exponent rules that you've learned before. So when you're multiplying the bases and they're the same, we're still going to add the exponents. So I have e, 5 plus 3 is going to give you e to the 8th power. And you did that without a calculator. We're not looking for a decimal version. That's because you have 5 e's, then you have 3 e's. That's a total of 8 e's. Here we're using the same exponent rules you've done before. You're going to first work with your 18 and the 2. 2 goes into 18 9 times. Your bases are the same, so you're going to subtract exponents. 6 minus 4 is 2. So this is 9e squared. Now we get here to number 3. I'd suggest to you to pause the video, give this one a try, and see how you remember working with your exponent rules. So we're going to come in, we're going to take a look at the exponents that we have. This is 4 to the first power. This is e to the 3x power. This is called a monomial, so we are allowed to distribute it through. You're not allowed to distribute into a binomial, but you are allowed to distribute into a monomial. So when you distribute in, we're going to get 4 squared, and we're going to get e 3x times 2. So that's going to be 16 e to the 6x. Not 6x squared, just 6x. Now we can use our calculator. With your calculator, down here next to the 4 button is e to the x. So second e to the x, near the 4 button. We're using an exponent of 3. So that is 2.718 times 2.718 times 2.718. That's going to be 20, apparently 20.09. E to the exponent of 0.3. Now if this was e to the first power, it would be 2.718. This is e to the 0.3 power. So it's less than 1. So I'm expecting an answer that is less than 2.718. 1.3. If we're rounding to the nearest hundredth, tenths, hundredths, thousandths. Let's take a look again. We're rounding to the nearest thousandths. So tenths, hundredths, thousandths. The 8 is going to make this a 10. The 10 is going to make this a 5. So 1.350. And if we look back at this one, if we did it to the thousandths, tenths, hundredths, thousandths, this would be 0.86 to the nearest thousandth. When we talk about graphing, We've talked about exponential growth and exponential decay before. This function, A is like the A's that we've worked with all year. E is the base to the power of Rx. So this is exponential like we've been working on. So the graph of the function has a horizontal asymptote. Because this is 2, it's greater than 1, we know that it's going to be a growth function. And it's going to come down and it's going to approach the asymptote at 0. We will have exponential growth as long as this stays greater than 1. And that's going to stay greater than 1 if we have r times x, and we keep that a positive value. So if a is greater than 0 and r is greater than 0, we're going to have exponential growth. If r is less than 0, then we're going to have exponential decay. To graph these, we will use a calculator because our base is 2.718, and that's not even accurate. To do any calculation to that, we practically need a calculator. So we're going to use a calculator to graph these also. So go to y equals. Now we've got things typed in. What I would suggest to do is hit second plus 712 to clear your calculator so we don't have anything getting in our way. Go back to y equals. Got a clean slate. We can type in this whole equation. 2 e to the x 0.6x. You don't even have to worry about going to the graph. Just go to the table. And we typically look at the values of -1, but you can move that even further if you like, so you can be a little bit more detailed, looking at both directions. For this one, I guess that doesn't matter that much. But -1, 0, and 1. At -1, we get 1 point. It would round to 1, 0. When x is 0, we're at 2. When x is 1, we're 3.64. So we know that this is going to be exponential growth because the r value is greater than 0. So to graph this, at -1, we're up just above 1. At 0, we're at 2. And at 1, we're even higher than 3.5. So we connect those dots, and we know that this would be approaching our asymptote, which we should draw in here as a dashed line. You must label it on your graph. We've talked about that every time. So the domain, what x values are we allowed to look at? All real numbers. What answers are we getting? We're getting just positive numbers, which is y is greater than 0 or 0 to infinity if you're using interval notation. It does not include 0. So it's a rounded bracket at 0. The asymptote, we're aware, is 0. That's why we have a rounded bracket at 0.
Is that because x is 0?
we can never reach 0 because it's a little tough to discuss it in terms of E. Even here, this is not 0. This is this is 6 decimal spots to the left. That's with the e to the negative x. This is times 10 to the negative 6. So left 6 spots. So 0.000001. That's what that number stands for. So it's just very small. If you're wondering about why doesn't it ever hit 0, think about taking a number like 50, divide that number in half, and keep dividing that number in half, and you might realize that if you're cutting a number in half, you're never going to reach 0. You're never going to reach a negative answer. Now, you might consider this to be negative, but like I said before, it's not negative. It is telling you to move the decimal spot 6 units to the left. 0.0000014901. And behavior. As x approaches negative infinity, as we look to the left of the graph, what is the y value doing? It is definitely not going negative.
It's approaching 0.
It's approaching 0. As x approaches the right, as it goes to the right, as x gets bigger, what is the y value doing? It's going upwards to positive infinity. Okay, our next graph. Notice here that the r value is less than 0. So that means we would expect this to be a decay model. This should be dropping over time. Now, we're not going to graph x plus 1. We're not going to graph the negative 2. We're not going to graph the translation. So we're going to make our table using just e to the negative 0.35x. In this case, you may want to have more values to the left so you can get a good, accurate recognition of what's happening as x gets smaller and smaller. So your graph looks good. So when we hit y equals, we remember we had a graph in there, but we didn't change any window values or anything, so we can just clear that. This is e to the negative 0.35 x power. We're not doing the translation right now. We're just putting in what would be considered the parent function. And we do second table or second graph to show the table. Let's get back. So at negative 3, we're at 2.8, 2.9. At negative 2, we're at 2.01. At negative 1, we're at 1.4. At 0, we're at 1. And at 1, we're at 0.70. So you can extend your table out if it helps you draw a better graph. So let's take a look. Normally, we would be at 0 with a height of 1. 1, we're at 0.7. And at negative 1, we're at 1.4. If this is what you had, and that's all the dots that you put on your paper, you wouldn't know how to curve this up. You would think that it would keep continuing up. But if you look at your other values, at negative 2, we're at 2. And at negative 3, we're at 2.9. You see that it's not really curving up all that quickly. We're going to have the asymptote here. Well, okay, take that back for a second. Sorry. This is an asymptote of the parent function, but this actually has a translation to it, doesn't it? So we like to save the asymptote for the translation. Very good. The h value is negative 1, and the k value is negative 2. So this is going to go to the left 1, and this is going to go down 2. So each one of those dots that we did, to the left 1 and down 2. Left 1, down 2. So that's curving through, and we'll also approach an asymptote. The asymptote's going to be the k value. The asymptote's going to be down at negative 2.
So the asymptote always the translation?
It's always the translation, the k value. And there we have it. You graphed it. And since we did 2 graphs, you can come through to show your final graph was that one. And it's good to write in the equation. Y equals e to the negative 0.35, parentheses, x plus 1 minus 2. Any questions about that? So next we're going to talk about compound interest. We've talked about how the formula for compound interest has been y equals, or a lot of times we call it a equals p 1 plus r over n, nt. That's if it's compounded monthly or daily, weekly, quarterly. But here, we're going to compound continuously. So compound continuously is when you use the PERT formula, P-E-R-T. So your base is E and your exponents are RT. When do you use this formula? You use this formula when you're using continuously as a compound interest. That's what you're focusing on. So what's the balance after 1 year if you put $3,500 into an account and get 4%? %, so you don't add 1 to that or anything. 0.04. And the years that we're talking about is 1. So you can type that into your calculator. 3,500 e to the exponent 0.04 to the first power. And that gives us 3642. We would expect that there would be growth in the number because your exponent is 2.718. Through 3,642.84. Now we're going to do a balance of 5 years. So you can retype that, but let me show you something. Down here it says entry. What was your previous entry? So if we hit the second key and enter, which gives you the entry, you're going to see that it brings up the previous thing that you typed in. So then you can come on over and just turn that into a 5. That might speed things up for you. 3,500 e to the 0.04 times 5 is approximately 4,274 and 91 cents. Okay, see if you can get your calculator to give you these values. Last one. You discover a new bank that pays 6.5% interest. Therefore, you decide to invest even more money. What is the new balance after 3 years? So go ahead, pause the video, see how you do with this. When we look here at the interest, we are compounding continuously. Continuously. That means we're going to use our formula we've learned about, called the PERT formula. We're looking at for the value of the account when we're investing 4,800, 6.5% means that we're going to move the decimal spot 2 to the left, and we're going to call it 0.065. And we're doing this for 3 years. So you need to write that down, not just an answer. Got to show some work. So 4,800 e to the x 0.065 times 3. 5,833. That's approximately 49. These are dollars. Good job.